All right, before we get into more complicated mathematics, I wanted to do two more ice table examples where we're just practicing our setup. We're making sure that when we do have simple algebra, we're proficient enough in it to solve for unknowns. So, sorry. Essentially, what we have here is a reaction. Now, later on in the semester, we're going to see this reaction is actually a base reaction, or how a base behaves in water. That's not important right now. The nice thing about this chapter is you're given the reaction in full, and then you're given some information about it. We're given a Kc, we're given an OH minus concentration at equilibrium, and we're given, okay, what is the initial concentration of CH3NH2? Okay, so we're given a target unknown to solve for. So again, it looks like there is some unknowns going on here. It looks like we should organize ourselves with an ice table because we have a K to use. So let's do that. I, C, E, line across, and then dot, dot, dots. So hopefully you're getting used to manipulating these and setting these up. There's a very simple thing we have to do right off the bat. I'll give you a second to think about it. Hit pause if you need to. All right off the bat, we know we can get rid of H2O liquid. Okay, so we know that right away. We're going to put a big X there. We know it's not going to affect our equilibrium calculation. We start to read about the information that we're given, and we're actually given that this down here, the equilibrium for OH minus, is 9.0 times 10 to the minus 3. Now, we're not given any initial information about these two species, and we're told that there is an initial concentration of CH3NH2. All right, it's just we actually have to calculate it. So this becomes our X, it's our unknown. We're not given information about these, so these become 0 for the I information. All right, now we can do Q versus K. Hopefully you can see by now, real quickly, Q is equal to 0. Q definitely then is less than K. So we know which way the equilibrium is going to shift. We know the equilibrium is shifting towards the product side, right? We know that at equilibrium, we're going to have more product at the end. And we can already see that here, okay? Equilibrium is going to move towards these zeros. All right. Well, if I think about what has to happen here then for C, I'm going to lose a certain amount there, and I'm going to gain certain amounts here. Now, we would normally put like a minus y here, or plus y, because we don't want to use an x because x and y might not be equal to each other. But, I mean, we kind of know what our C looks like anyway right away because we know that I plus C equals E. So if I have a 0 here, this right here in the change portion of our ice table, this must be equal to 9.0 times 10 to the minus 3. That's the only way to get I plus C to equal E. So hopefully that makes sense because then we can look over here. Well, wait a second. This is a 1-to-1 stoichiometric sort of coefficient ratio. One of these and one of these, right, are involved in the balanced chemical reaction. So if this, if this started at 0, it's going to change in the same way. Just like we would put normally a minus x and a plus x and a plus x here, or plus y and a plus y here. If I know what that number is, I'm going to put that same number there. So I plus C equals E. Oh yeah, if I start with 0 of this, and I start with 0 of this, and I end up with some amount over here, it has to be the same amount over here. So now I come to this side of the ice table. Well, if I was going to be putting plus x's here, or plus y's there, then over here there's also a stoichiometric coefficient of 1. So over here, because of the direction of equilibrium, I'm going to put minus that same number that we've been seeing pop up over and over again. So my E is really x minus 9.0 times 10 to the minus 3. So we used our I information to get our Q. It dictated how we were going to fill out the rest of our ice table. And now once we have E, we know, and hopefully you're seeing a pattern by now, that we can feed this into our expression for K. And Kc is 3.7 times 10 to the minus 4. This is going to be equal to concentration of this, multiplying each other, both raised to the first power. So that looks like 9.0 times 10 to the minus 3 times 9.0 times 10 to the minus 3. Oh, that's the same as squaring this. Divided by 1, because the H2O doesn't matter, times x minus 9.0 times 10 to the minus 3. So again, I like to just kind of show this example to make sure you understand that, okay, sometimes we have an unknown here, sometimes our unknown is in our E spot. In this situation, we could infer what our change was based off the stoichiometry of the problem. Now here's an equation with one unknown, this x. So I'm going to give you the answer. So practice your algebra skills and your algebra manipulations. What we get here at the final answer is that CH3 NH2, the concentration at equilibrium is equal to 0.23 molar. So again, I'm not doing the algebra, I'm leaving it for you to practice, but it's a nice little example to see in terms of another setup. I'd like to do another setup problem that yields a sort of a little bit on the easy side math. And then in the next video, we're going to get into slightly harder manipulations or slightly harder mathematics that we see, but it's nothing to be afraid of. But again, just in the realm of sort of practicing ice tables, let's do a gas phase reaction. So let's look at this reaction where we have CO gas plus 2H2 gas in equilibrium with CH3OH liquid. And let's say that the only thing that I give you for this problem is that Kp is equal to 2.25 times 10 to the minus 4. And what I want to know is, what's the pressure of CO at equilibrium? And what's the pressure of H2 at equilibrium? Oh, that's all that you're given. But even though that's all you're given, just this Kp in this reaction, this is something, again, we can organize with an ice table. We can use our assumptions that we've been using and we can solve it. Again, doing a calculation, we have a K given. We're trying to solve for unknowns, organize our thoughts with an ice table. Again, the very first check that you do is you see if there's anything we can eliminate from our ice table. I'm not even going to give you a chance to pause this time. We know we can get rid of that liquid. So now, if this is the only information that you're given for the problem, what do we know about the initial pressures of H2 and CO? We know that they are 0. That's implied with the problem, okay? Because you're not given an initial amount of each. So then, what's Q in this case? Q looks like 1 over 0 times 0 squared, 1 over 0. Again, Q is infinity, so Q is definitely bigger than K. And we see with this example, just like the other examples, that when there's zeros, equilibrium shifts to make those zeros go away, to make those zeros actually go up in value, right? Q is greater than K, we have too many products, we shift in that direction. So take a second, try to fill it out yourself. Right, I'll pause just a bit. You can pause the video. Right, so we should be able to put, with confidence now, a plus x here and a plus 2x here based off that stoichiometry. I plus C equals E. I plus C equals E. So now, if I look at what I'm after, the pressure of CO at equilibrium, well, I'm using a Kp, so whatever answer I get for my x is going to be a pressure. It's going to be in atmospheres, right? So the pressure of CO is x. My pressure of H2 at equilibrium is 2 times x. So the rest of the problem is, can I figure out x? Because x is the answer to this part, and 2x is the answer to this part. Well, you guys absolutely can solve this. Because you know, once you fill out the E portion of the ice table, and again, the CH3OH isn't going to matter, you can make an expression with this K. So K is going to be equal to 1, where is this coming from? Oh yeah, big X, that's why we put it there, over x times 2x squared. I'm going to stop here because I made a mistake. And it's a common mistake, right, that students will make. Now, the reason I like to point this out is because it throws everything off if you don't catch it. So hopefully you can see that this pressure right here is 2x. So what do I have to square? I have to square this whole thing. So then what we're left with is algebraically 2.25 times 10 to the minus 4 is equal to 1 over, there's going to be x here, there's going to be two x's there, so I'm going to get an x to the third, and I'm going to also get a 2 squared in the bottom, 4x cubed. Now algebraically, let's do a little bit of a rearrangement, because remember, as soon as I solve for x, I know what these values are here. So this looks like 4x cubed is equal to 1 over 2.25 times 10 to the minus 4. So just remember your algebra involving fractions. I multiplied this to this side. I brought this over here in the denominator. This you should be able to solve. Now, somewhere along the way, you're going to have to use like the caret and the 1/3 in your calculator to solve for that x, all right? But before you get there, you're going to have to figure out what this number is, divide by 4. But you fill in the gaps. And remember, if you want to take like the inverse of a cube root, this is what you're going to do in your calculator. What you end up getting for x is you end up getting that x is equal to 10.4. So again, once we get that, we know what our answers are. The pressure of CO gas is equal to 10.4 atmospheres. The pressure of H2 gas at equilibrium is equal to 2 times that. So it's equal to 20.7 atmospheres. So you might be asking yourself, wait a second, 2 times this is not that. Remember, when you do this, you're not going to round. And this is really 10.357 atmospheres rounded, right, to that decimal point right there, paying attention to significant figures. 2 times that is 20.7, right? And so that's what you end up with. Just again, using our significant figure rules, we wouldn't round until the very, very end, okay? So just another bit of practice. Hopefully you can practice the algebra and the setups and start to get comfortable with ice tables.